Hello everyone, this is Xingfeng Shao from University of Southern California. Today I'm going to talk about BBB water exchange rate and permeability mapping using multi-delay diffusion-weighted pCASL. So I have nothing to disclose. So ASL is a non-invasive technique to measure the cerebral blood flow, and we can use it to monitor the label blood flow coming from the label imprint to your target voxel, and we can monitor the exchange of the blood across the BBB, the blood-brain barrier. So if we look at this voxel, so when the signal arrives, the majority of the signal remains in the capillary space and starting exchanging into the tissue space with the exchange rate of kW. So if we wait a certain time, we usually call it post-labeling delay. So majority of signal goes into the tissue space, while only about 20% signal remains in the capillary space. So here's a typical perfusion image we can get in the PLD of 1.8 seconds. So if we apply a small diffusion gradient, as demonstrated in our previous study, so we can successfully nullify the capillary signal, and the perfusion signal with diffusion weighting contains only the tissue signal. The reason we can do this is because there's about 100-fold difference in the apparent diffusion coefficients between the capillary and the tissue compartment. So with these two maps and some modeling, we can use to quantify the KW map very successfully, and we have shown some clinical evaluations. So if we wait even longer, so at a longer post-labeling delay, so this tissue fraction equals to the total extraction ratio of the water, and we can calculate the PSW, the permeability surface product of water, using this simple equation. However, the PLD is usually required to be longer than 2.5 seconds, so this is leading to a very low SNR, which may limit the reliability of our EW or the PSW measurements. So the goal of this study is to propose a new post sequence to achieve higher spatial resolution, and we also propose a new acquisition protocol and a robust algorithm for KW and PSW quantification. So in our previous study, we use a non-CPMG diffusion preparation. So we utilize the dephasing and rephasing gradient pairs to make the sequence robust to the phase induced by the motion during the encoding duration. So which can be used for single shot acquisition with a resolution about with a relative thicker slice, about 8 millimeter. So but it's very robust. So however, there's one limitation in this technique leading to the half signal loss and not suitable for segmented radar, leading to limited spatial resolution, especially in the slice direction. So we proposed a new idea. So this year we tried to modify the existing crusher gradients on two sides of the refocusing process of the gray radar. So here you can see the orange lobes are the crushing pairs. So we can replace these crushing pairs with M1 compensation using this -A to A and A gradient pairs to compensate M1 motion. And also we can adjusting the timing and amplitude of those gradient pairs to achieve the B values we desired. So since we only need a very small B value about 50, so the duration of each A lobe is only 3.9 milliseconds. So we can also adjust the amplitude of these gradients while keep the same timing to achieve the B0. So here's our imaging parameters. We have 36 slices with 20% oversampling, so we can achieve an isotropic 3.5 millimeter resolution. So we have a threefold, actually 3 segments along Z direction, but we apply the TGV reconstruction to each segment to achieve a threefold acceleration. So our labeling duration is 1.8 seconds. So we have 5 post-labeling delays from 1.5 seconds to a very long PLD about 2.7 seconds. So we have 18 label control pairs for each PLD. So here are the perfusion map acquired MPLD about 1.8 seconds using the proposed technique. You can see there are 36 slices, excluding the oversampling slices. So our previous map technique can only achieve 12 slices. So here are the TSNR map, as you can see, with the proposed technique. TSNR is almost 4-fold higher compared to our previous technique, which means we can use the proposed method to achieve higher temporal SNR, which allows more reliable measurements, especially at longer post-labeling delays. So we scanned 3 healthy subjects. So the first row, so each column is a perfusion image acquired and a different post-labeling delay from 1.5 seconds to 2.7 seconds. So the first row is without diffusion weighting, which means it's a typical ASL perfusion map which contains both capillary and tissue compartments. So the second row is we turn on the B50 gradients. So we can see the signal intensity is slightly lower than the first row, so which is because the capillary signal was not. But you can notice that at a longer post-labeling delay, the difference between the first row and second row becomes smaller, which means the majority of signal already enters into tissue space even before we turn on the diffusion weighting. So here's a perfusion signal acquired and 5 post-labeling delays. The blue curve is with diffusion weighting, the tissue signal, and the black curve is without diffusion weighting, which contains both capillary and tissue signal. So and those 2 long PLDs, you can see the signal intensity are pretty much similar to each other. So here's a vascular fraction, which is the ratio between the blue and the black curve. As you can see, it's about 20% and a shorter post-labeling delay, and it's stabilized around 5% and PLD about 2.4 and 2.7 seconds, which means we can estimate total extraction ratio from those 2 long PLDs. And also we can calculate the PSW based on the EW we quantify. So from the PLD of 1.5 seconds to 2.4 seconds, it's captured the dynamic of the water exchanging from the capillary space to the tissue space. So we can, using a very simple but robust linear regression model, as I'm going to explain later, to quantify the KW from the delta MC signal acquired and 4 post-labeling delays. And we can also quantify the CBF since we have 5 post-labeling delay using a multi-delay feeding model. So actually, here's the explanation is how we propose a very simple but robust the linear regression model to quantify KW. But due to time limit, if you're interested, please come to my talk on Tuesday in the ICC Cactus Suite 1011. So here are the 5 slices of the CBF, KW, EW, and PSW maps. So the global average values of the CBF, KW, EW, and PSW match the literature of the KW and PSW studies very well. And you can notice here, the EW is about 95%, which indicates the PLD about 2.4 and 2.7 seconds are sufficient to estimate the total extraction ratio as well. So again, if you're interested, please come to my talk on Tuesday. And thank you so much.